So what I will do today is to take you through a journey about what is happening in the market from a trend perspective, what is the impact of that one on applications, and how does that one impact materials, which is in this type of applications, primarily connectors, where the plastic is used in insulation materials, essential for the safety and reliability of the good functioning of these connectors. So if you look into a market, electronics market is one of the most dynamic and one of the most speedy segment which you can imagine. Every day, every week, there will be a tremendous amount of new innovations. On the left side, you see applications which gradually are basically declining. Something like desktop computers, even gaming consoles, which are still very popular. With all the cloud gaming, you can already expect that hardware at home is declining at a certain time. Something like an SODIMM memory or a CPU socket where you still have hardware components in the future will be directly printed on the PCB as a chip, and therefore also these applications will decline. On the right side, you see some of the applications which in the future are seeing a very strong growth in the market. For today's discussion, we will not touch this whole interesting area. We will only zoom into one area, which is connected home. Connected home is all about interconnecting all the devices that we have in our home. Starting from the central switchgear area that you are working on, all the way to the end application like a washing machine or an oven. Why? Because it makes the life of a consumer like us more convenient. So the industry is bringing in more and more technology to make our life easier, to interconnect all of these devices. But these interconnections will also change a lot. One of the things which is very important if you talk about connected home is the way how it is installed. This could be one concept with using voice recognition and type of personal assistance to control all the home. Yeah, from a smoke detector all the way to a washing machine or the door opening, thermostats and central heating. These devices are not futuristic devices. This whole move is currently happening. In this interesting, exciting environment, there is one application which is extremely critical. It's in itself actually a very boring application. A simple connector, which exists already since a long time. But this connector is the core backbone to interconnect all of these devices, which is sitting basically one level behind the wireless interconnects, which you typically don't see. But it's a fatal part of the backbone of interconnecting all of these devices. If you look from a design perspective, a connector designer is looking for increasing safety, increasing reliability, making designs smaller to cut out space, improving processing so that also from a molding perspective it becomes easier. At the same time, if such a simple connector would be designed wrongly, the entire application can fail. And now imagine we as a consumer are in our houses, sleeping with our family, with our children in the sleeping room, and the unattended appliance product, which is one fundamental part of connected home, like a washing machine, sits in the cellar, and an electrical failure leads to overheating, to a shortcut, and to a fire. And we are sleeping just one level or two levels above this fire. The whole house can burn, our family can die, our children can die, caused by a simple connector. So taking care of a good safety and reliability in these connectors is fundamentally essential for all of us, not only in the business environment, but also as a direct consumer, which is at the end buying these products. Now, connected home has one big change to the standard model as it is used now. These devices become gradually more unattended because it's connected to the smart grid. It means that basically a washing machine can turn on and turn off at any time of the day. There is no more need for us to be present. You can control it via your smartphone, or it just gets information from the grid. Electricity cost is very low. Now it's time to start washing, for instance, and then the washing machine starts to operate. So there's no more need for the consumer to be present. Today, our presence can still interrupt if there's a big failure happening, but this will be basically impossible in the future. So this unattendance increases significantly the need for pushing safety and reliability much, much higher than it is currently used. Yeah, so a dramatic effect. And now the other important number that you should keep in mind is that by 2020, which is basically now, there will be approximately 30 billion connected devices in the market. So not only that it happens and increases safety and reliability, but the amount of interconnections is increasingly growing in the future. So a potential risk is dramatically increasing. Now the key interconnect is a connector. This is just a visualization of some of these connectors. One of the most common standard for these connectors is called Rast. It's a German technology for Rasteranschlusstechnik. It has become a prime global standard in the meantime. Even in automotive, Rast is currently started to be used. Makes interconnections very easy because it has a color coding. So making a mistake in interconnecting becomes basically very low. So therefore it's a common standard which is very popular. Now this kind of connectors you find in all kind of appliance devices. From an oven to a washing machine. Now talking about safety in reliability, there is basically one big factor which is reducing safety and can be the root cause of a failure. And that is electrical tracking. Electrical tracking happens if in between of two electrical interconnects, like two connector pins, where you have basically a plus and minus pole, you get contamination. These interconnects are separated by an insulation plastic, which is of course non-conductive, but if you get some contamination at the surface of that plastic insulation material, like dust, moisture, sweat, particles, that can be the root cause of a track, of an electrical track. Each of these dust particles has ions in the surrounding. And it is a process which is accumulating. Over time, more and more contamination gets populated at the surface. At a certain time, the ions are generating a closed path and a spark is generated. That tracking or sparking can basically lead to carbonization of the plastic surface. Now, carbonized plastic surface basically means it becomes electrically conductive. So with that contamination, over time, the surface of the plastic becomes electrically conductive. And if this conductivity reaches a certain onset level, then you get a spark and you can get a fire out of that one. There are fundamentally three ways to avoid that spark. Way number one is you take your electronic circuitry and you put it in a box. You completely seal it from the outside. So contamination cannot reach these critical components inside your circuitry. It's a very efficient way, but you need quite some space for that. It's an extra processing step. It's extra cost. So not every designer, every manufacturer wants to do that one. Another way to reduce risk is you keep your circuitry very low profile, very easy, but you upgrade your plastic that you use in these interconnects. And you go from a low CTI material to a high CTI material. So you allow contamination, you allow the generation of tracks, but you avoid the formation of a spark or of an electrically critical situation by having a plastic which is significantly more robust towards tracking. The effect is pretty similar. This way you can live with a low CTI material. CTI, by the way, stands for Comparative Tracking Index. It's a material parameter. The higher, the lower the risk. But it's not mandatory that you need to have it. It's just risk mitigation. Different options can live with different CTI values. And a third way to avoid tracking is you basically increase the pitch between your pins. But in a connector, the pitch, specifically if you have a standard defined behind that one, you cannot just increase the pitch. So what a designer is doing, he is increasing the so-called creep distance. The actual pitch remains the same, but the surface of the plastic can be increased. For instance, from a flat type of surface to a rib type of surface. The effect is the same as if you would increase the pitch of the connector. The more the creep distance, the lower the risk for a tracking. Three ways. The creep distance cannot always be done because there are design restrictions. Sometimes there is not space enough. This one cannot always be done because it's a pretty expensive and space-consuming way. Changing the material from a low CTI material to a high CTI material is the easiest way to cover this risk factor. You just need to change low CTI plastic by a high CTI plastic. Now, to give you a feeling of what the difference between a system with a low CTI material and a high CTI material can be, have a look to this video, 2 minutes. Because the video can explain it significantly better than I can do. Just look at the video, also very fine. Lots of electrical failures in appliance devices in the market. If you Google for that one, there are millions of devices which fail. Do you note the tower in London, which was catching fire some time ago, with a lot of fatalities linked with that one? The root cause was a white good appliance product at the end that failed, and which led to that fire. So now, if you look into the cause where this kind of issues can happen, a simple connector can be the root cause of such failures. And you see a comparison between a connector with a low CTI material to a connector with a high CTI material. So this is simulation of what happens in real life. The higher this number, the longer the lifetime of the connector is. The more it can survive contamination from the outside. And you see that already after some time you get spark formation, smoke formation. This is just the onset of catching fire. This is the root cause why appliance products get fire. While here nothing is happening despite surviving significantly longer. Low CTI material, high CTI material. The impact, fire towards non-fire. Big effect. Nothing happened in the design. It's still the same product, still the same device, still the same design of the connector. The only thing that happened is plastic A has been upgraded to plastic B. Small but dramatic, big impact. So now the tricky thing is, how does a material supplier support to do that one? Now, as a designer, typically companies look into UL cards, yellow cards, where basically materials are molded into plugs. Plugs are tested according to glow wire testing, and then you get a certain number, certain figure for the glow wire testing, and everybody is happy. We have found out that this is actually not sufficient, not enough. We go significantly more than the typical approach of just providing a yellow card and a material. We also do the testing on real connectors, because we think there's a significant difference between a plate and a connector. At the same time, we also do full simulations of real life usage. This is actually extremely important, and I will show you why. Yeah, so we take the full way, all the way fully integrated up to the final end application. Now, to give you a feeling about what that means, you can compare here two different materials, yellow cards. One, and both is our DSM materials. Yeah? Material 1, material 2. Do you note any differences here in the yellow card figures? This meets 960, but also this one meets 960. This is all the way at different thicknesses, up to 1.5 millimeter, which is typically done in the industry. This one also. So on paper, you may think both of these materials are actually doing a good job. So as a designer, you start to use that material and you think safety done. But be very careful. Remember the fire, remember children sleeping at the top of the roof. This is how we do the testing. as I mentioned, not only in plates, but also on real connectors. At different temperatures, glow wire testing. Yeah? Standard test, nothing spectacular here. Now, if you compare the results of such glow wire testing, so here you see the glow wire ignition temperature plotted for different thicknesses of these plates. Typically, companies measure at 0.4 millimeter, 0.8 and 1.5 millimeter. What you see is material number 1 here with the yellow coat is actually a lousy material. The glow wire ignition temperature is very low. So just doing paper exercise, you say not good, out. But then you have these 3 materials. On paper exercise, they all look pretty similar. And the designer says, okay, I take the cheapest one, I take the easiest one, I take the one that I always took, no big deal for me, and he can take any. If you go from 1.5 millimeter to 3 millimeter thickness, just by enlarging the plate thickness a little bit, you suddenly see a big differentiation between these materials. At lower thicknesses, you don't get any differentiation. All of them perform pretty equal, 960. Just by slightly increasing the thickness of your plate, suddenly you get a big differentiation. But not too many people are doing that one. We do. And I think it's important that you also know about that one, why it is so relevant. What we also do is we don't only measure glow wire ignition temperature 5 seconds on plates, but we even go one level higher in requirements. We measure no flame 0 seconds, which is a bit more a tough test. See that immediately when you go from this test to this test, you also get differentiation even at the lower thicknesses. So going towards a more aggressive test and going towards thicker plate thicknesses is very important. Only then you will be able to differentiate between good material and bad material. If you don't do that one, all of them will be pretty okay. The only one that you can differentiate is the really lousy material, but the rest is all the same performance. Yeah, so very important to differentiate, to choose the right test and to choose the right thickness of your plates. One thing that we also do, and that is important when you do your design of your applications, that we don't only test on plates, but we also test on actual devices, on actual connectors. You see that if you combine a measurement and change thickness from thin plates to big thicknesses of 3 millimeter, this test is pretty much equivalent to a real connector test. While on too low thicknesses, nobody knows really how good the materials are. In a real connector, you can get very different performance. This one can burn while your yellow card says all is okay. But if you increase the thickness, you get basically the same output like on a real connector. So very important that you measure at thickness, or that we as a material supplier give you data which is the right test representing basically your application. If you do that one, we can mold connectors, or you can mold connectors which are showing no flame even at 900. So it's not glow wire ignition temperature, it's the GWT on the end product, which is actually the real test for you. Not just on the material, but on the actual end connector. So what is important, if you look into the matrix of glow wire ignition temperature on the one scale, CTI on the other scale, and flammability on the other scale, the holy grail that every designer wants to have in the connector industry is a material that gives him a V0 all the way up to 1.6 millimeter. So flammability, very important. At the same time, he gets a glow wire ignition temperature larger than 850 with no flame. This axis. At the same time, he gets a high CTI larger than 400 on this scale. And he also achieves the glow wire test or passes on the end product of larger 850 while no flame is formed. This is basically the magic that so far nobody could deliver. Now you have a very nice solution. Now if you compare all of these parameters, parameters, like you saw in the presentation, for different materials. This is the two DSM materials. These are two very incumbent, commonly used competitors in the market. The requirement was to pass on all of them. Yeah, this axis that I just showed. Companies which deliver high on glow wire performance, they fail on flammability. They only deliver V2. Or they are very good on V0 and glow wire, but the CTI is very low. Only this material is passing all of them. So you have basically two options now. If the design is boxing it in a protective box, you can go for a low CTI material or standard CTI material. If you want to take out design cost and reduce the amount of components in your design and put the connectors directly on the PCB, even if your appliance product is sitting at high humidity or high temperatures for a long time with a lot of particles in the air, you can go for this material, which is delivering highest flammability, highest glow wire performance on end products, and highest CTI, and all in one material. So in appliance industry, DSM is active since many, many years. We have a complete roadmap how we evolved. This achievement is not coming overnight. We have built on many years of experience up to coming up with a portfolio which is basically delivering the holy grail that everybody in the connector world needs to have and wants to have. Why? In order to reduce the risk of a fire so that we as a consumer can safely leave our home while the appliance product is running unattended. For those of you who are interested in some more details, there's also more documentation available, technical articles which describe much more in depth than what was discussed here in this short presentation. This is all available online and also as a hard copy version. And to summarize, 3 things that you should keep in mind about DSM. Because if you compare, there are many plastic companies. Specifically here at the K, you can go from one hall to the other one, you come from one company to the other one. So you say, why should I do something with DSM? I can also go to another company. Indeed, there are many companies which are very similar. Some of them are even bigger than DSM. But there are 3 key items which are really characterizing DSM. DSM is extremely focused on research. Already the fact that we don't only provide plug tests on yellow card base, but do all the way to end product testing on the end application is the outcome of significant deep research and understanding the needs of these applications. We invest very strongly in technology to improve in a nice roadmap and deliver the needs that you as a customer have. And we combine it with a very strong application expertise so that we take from a base research, translate that into product development and combine it with the application of the customers and really match it to the needs of our customers. Why do we do that one? We do that one to have safety and reliability deep in the center of all the stuff that we do.